So let's go ahead and begin. As I mentioned in our last class meeting, we're going to kick things off with a little example here. Just to see how all this stuff works, and then we're going to get into some other things. So we're still really talking about how an induction motor works and all of that kind of stuff. So let's say that we have a 50 horsepower three-phase 60 hertz induction motor. And it operates at a rotor speed of almost 900 RPM. When unloaded, and a speed of 873 RPM at full load. I want us to determine the number of poles of the motor, B, the slip frequency of the motor. That's the last thing that we talked about at the end of class on Tuesday. I may have called it the electrical frequency of the rotor, but slip frequency and electrical frequency of the rotor are literally the same thing. So I'm just going to call that F2. And then lastly, the torque. Developed by the rotor. And I'm going to call that T shaft. So for these first two things, it's just exploring relationships of what we did towards the end of our last class, right? So our solution for part A, sorry, I don't know why this thing isn't scrolling. Our solution for part A is simply to use that relationship that our synchronous speed NS is equal to 120 times our stator frequency divided by the number of poles. So if we rearrange this guy, it should simply be that our number of poles P is equal to 120 times our stator frequency over our synchronous speed. So based on the information given in the problem statement, what is our stator frequency? 60 hertz, absolutely right. Divided by 900, so that's absolutely right as well. So, sorry, what was that?
It's 8.
Is what?
The number of poles.
The number of poles is 8. This is something that we were talking about yesterday, so there is a handy way to do this. Effectively, if you have a 2-pole motor at 60 hertz, it's going to have a speed of 3,600 RPM. If you have a 4-pole motor, that's going to cut that in half, so it's going to be 1,800. If you have an 8-pole motor, that's going to cut that in half, so it'll be 900 and so on and so forth. So there is a very simple relationship to get there, right? So you'll get to a point where if you see a 900 RPM speed, you'll know, oh, that's an 8-pole motor from the jump. You didn't even need to do the math just on how that's related. All right, so we've got our solution for part A. Like I said, pretty easy. Part B, so I want us to recall from the end of our last lecture that our electrical frequency or our slip frequency is simply S times our stator frequency. So we have our stator frequency of 60 hertz. So now we just need to figure out what S is, right? So S, or slip, is nothing more than the difference between our synchronous speed and our rotor speed divided by our synchronous speed. So that's 900 minus 873 over 900. That comes out to be 0.03, or you might often see the slip expressed as a percent, or that would just be 3% slip. Okay. So from that piece of information, our electrical frequency of our rotor is just 0.03 times 60 hertz, comes out to be 1.8 hertz. Okay. Our last relationship, we haven't talked about specifically here really yet, when we're talking about induction motors, but this was a relationship that was given to you guys when we were talking about electromechanical energy conversion way back at the beginning of that material, okay? So we're asked to find our torque. Well, our torque is just the ratio of our power developed by our rotor divided by the angular rotation speed of our rotor. So we're going to have to do a little bit of some unit conversions and stuff like here to make everything work out. So let's start with something straightforward. Which of the quantities that we're given here is related to the power of the motor? 50 horsepower, absolutely right. So we're going to put 50 horsepower up in the top, okay? So torque is usually measured in units of Newton meters. Okay, I'm just going to put that here at the end. Newton times a meter, where a Newton is an SI unit. So we're probably going to need to put horsepower, instead of having it in horsepower, we're probably going to need watts or something like that. Okay, so the conversion factor from horsepower to watts is that there are approximately 746 watts per horsepower. And now let's see what shakes out when we look at our denominator, right? So we've got rid of our horsepower, so we just have watts in the numerator. So ultimately, we're trying to figure out what our angular velocity is, and that is a quantity that's measured in radians per second, okay? So this is related to the rotor's speed. So what piece of information do we have about the rotor's speed under full load? 873. And sorry, let me specifically say here at full load. I forgot to mention that, but it should have been there. So we've got a speed of 873 revolutions per minute. So I'm explicitly doing revolutions per minute like this so we can see how the units wind up canceling each other out, right? So I could take this 873 revolutions per minute. If I multiply that by a factor of 1 minute per 60 seconds, and then there are 2 pi radians per revolution, what I'll see is that revolutions cancels, minutes cancels, and I'm left with an angular frequency of radians per second. Okay. So that's our conversion to go from our speed measured in RPM to our angular frequency. And what this is going to come out to be is 408 watt seconds based on these units, where a watt second is actually the same thing as a joule, which is the same thing as a Newton meter, our measure of torque. Okay, so this one was pretty straightforward. So let's get into bigger things. We guys good to flip to another page and start over and all that kind of jazz? All right. So I don't know why it started on page 4, so I'm just going to start back on page 1 and erase all that crap that I just did. Okay. So our give me some weird error I've never seen before. So before we get into a lot of math, I want to talk a little bit about power and efficiency. I forgot the I. So I'm going to make a little, I hesitate to even call it a graph here, but it's just a representation of what's going on in our motor. Actually, I'm trying to decide if I want to do this now or if I want to do it in a little bit. We'll do it now. I'll just introduce some things. Okay, so I'm starting out essentially on this side of the page. This is my input power, okay? And so this is going to be an electrical power at the input. I'm going to make a little note of that. And what I'm going to do here is I'm just going to make some notes on the things that are causing losses in our system, okay? So we've talked about some of these before when we talked about transformers effectively, and we also talked about some of them a little bit in our lectures on electromechanical energy conversion. But one of the main thing that's going to cause some losses is the windings of our stator and the windings of our rotor. So let's first take into account our stator copper losses. Okay, let me make this a little bit smaller here. So I'm putting an arrow down here. And this is just representing our stator copper losses. And then we're also going to lose a little bit of our power due to the fact that it takes energy to magnetize our core. So we're going to have core losses, just like we saw in a transformer. And so now we are about to, I'm going to call this guy right here. So I'm going to put a dashed line here. So we're effectively described all of the losses that are occurring in our stator. So if we're looking at this thing as an electromechanical energy conversion system, we've got our input energy into the stator, the losses associated with the stator. Now we're getting into the field energy portion of things. So this line essentially represents what's happening on at our air gap, okay? So I'm going to call this the air gap power. And I'm going to give this a symbol PAG. So this is the amount of power that crosses the air gap and is being converted into the mechanical power that's spinning the rotor, essentially. Okay. So after we cross the air gap, we're now in the rotor, and we know that the rotor has some windings as well. So we should see some losses associated with those rotor windings. So here are our rotor copper losses. And now we are at the point where we're looking at our mechanical energy of our system. So I'm going to put another dashed line here. where everything to the, so this point in our energy conversion process, we are looking at the developed mechanical power. And I'm going to call that P mech. And now we're going to start talking about our mechanical losses. So we are going to have losses due to friction. So these are typically lumped together as friction and windage losses. And then we're also going to have a term, and this is just a catch-all thing. This is literally just called stray losses, and it's literally just a lump term of any other losses that we might have experienced. So there's just kind of lumped here at the end, and then whatever is left over from all of those loss mechanisms is the power that we are able to output to our shaft of our motor. So I'm going to call this P shaft, and this is the mechanical output power. Stray losses, yes. STRAY. So we've talked about copper losses before. We've talked about core losses. So just really, really briefly here, I'll say PFW. This is our friction and windage losses. Occur because of air friction of the rotating structure and losses of contact with the slip rings on wound rotors. So realistically, they just introduce a little bit more resistance, and so we have to take into account those losses as well. Okay. And then our stray losses are literally just any other losses not attributed to resistive losses or our friction and windage or windage losses. So it's just literally any other losses we see where our output is a little bit lower than we expected, we just call it a stray loss. And we don't really worry about what that is. Okay, so talking about efficiency now, pretty straightforward. Our efficiency for our motor and motor is simply going to be the ratio of our output power to our input power. So this is effectively the ratio of the power that is delivered, that says shaft, not shaft, the power delivered to the shaft divided by the electrical input power that we have in our system. And then while we're at it, very quickly, we can have some torque relationships. So the mechanical torque developed. So that's effectively the torque developed at this point in our system before we have any friction and windage losses and things like that is going to be our mechanical power, Pmech, over our rotor speed. And this is going to turn out to be, and we'll talk about these terms in a little bit, our air gap power times a factor of 1 minus s over omega s times a factor of 1 minus s, which then comes out to be simply our air gap power divided by our stator field angular frequency. And we'll get into all these relationships when we look at an equivalent circuit and see why it comes out that way. And then lastly, the shaft at our torque is just the power delivered to our shaft divided by the speed at which, or the angular velocity at which our shaft is spinning. And we could also write this as P shaft over omega s times 1 minus our slip. So I personally, I like this big diagram like this because it helps me see effectively the process of the energy conversion, where we're stealing our losses from or where we're losing our power from and all of that kind of stuff. So usually when I'm working problems related to this, this is the graph that I'm going to look back at and just make sure I'm kind of following through the steps of that energy conversion to electrical energy, or from electrical energy to mechanical energy. So with that in mind, now let's start looking at, I'll skip this example for now. So let's start looking at this thing as essentially an electrical circuit. Okay. Yep. Yes, lowercase s is slip. All right, we good to go? Good deal. Okay, so let's talk an equivalent circuit model. All right, so in an induction motor, what do we have? So we have some input power. It is being fed, our input power is being fed into a stator coil. That stator coil is generating a magnetic field, which is transferring energy then over to the rotor coil. And then beyond the rotor coil, we wound up with some type of mechanical output power. We're going to focus on that interaction between the stator coil and the rotor coil for right now, okay? So what other thing have we talked about where there's energy transferred from one coil to another? A transformer. So we are going to treat an induction motor as if it is literally a transformer, a three-phase transformer, where we allow our secondary to rotate, because that's exactly what it is. So we have our stator windings, which is the exact same thing as a coil we might see in a transformer. And then for a wound rotor, system, we would literally have a three-phase rotor winding, which would be the exact same thing we would see in a transformer. But now, because there's torque involved and we have a way for it to spin, we're just going to let that secondary rotate. So I'm going to start by looking at our stator model. And this is going to be our stator equivalent circuit on a per phase basis. Meaning, technically speaking, there are going to be three of these guys, but because they're all identical, and I hope I imparted this upon you guys enough way back in 280 when we were talking about three-phase systems in a YY configuration, we only need to look at one phase to know what's going on, and that's exactly what we're doing here. Okay. So we've got our simple stator model, and it is going to look incredibly similar to the model we use for the primary side of a transformer, right? So I'm going to have a set of terminals over here. So this is where I'm applying a voltage to the stator windings. My windings themselves will have some resistance when I'm going to call just R1. They are also going to have some reactance, JX1, like so. I'm going to have some shunt components. So I'm going to have a core that I'm magnetizing. So I'll have some resistance RC. And then just like in our transformer, I'm going to have some reactance. My magnetizing reactance, JXM. And then over here on the right-hand side, this is my induced voltage E1. Okay. So let me label a couple of more things just really quickly here. So this is the current flowing through our core IC. This is our magnetizing current IM. This is once again going to be our excitation current, I lowercase e, and this current right here, I1, is our input current to our system. So I'm going to label these things just so that it'll be helpful. So R1 is the resistance of stator windings. Per phase, and these contribute to our copper losses, specifically our stator copper losses. X1 is our reactance of our stator winding. Also per phase. So this is representing flux leakage. RC is our core resistance, so resistance of the core. Also per phase. These contribute to eddy current and hysteresis losses, losses, like we talked about in transformers forever ago. XM is the magnetizing reactance of the air gap also per phase. And then once again, we have our voltage V1. So this is the terminal voltage of the stator windings. So this is what we have control over. This is the voltage that we are applying. And then E1 is the induced voltage across the stator windings. So this is the voltage that is essentially, scroll up. So this is effectively the voltage that we're going to see literally at those right-hand terminals where we're taking into account all of our losses, which are going to kind of cause some sort of voltage, internal voltage drop in our motor, okay? For what it's worth, this stator model is operating at a frequency, that looks shitty, of F sub S, okay? I'm saying that very specifically because our rotor is going to be operating at a different frequency, and we're going to have to figure out a way to take that into account, or a different electrical frequency, and we're going to have to figure out a way to take that into account when we put these models together, okay? So this is what's going on in our stator. So this is identical to the primary side of a single phase transformer. The only real difference that we're going to see is the size of these parameters. So in a transformer, we got to use that cantilever equivalent circuit. You guys remember that thing? And the reason that we got to use the cantilever equivalent circuit is because our excitation current, IE, was very small compared to our input current on our primary, right? Typically around 5% or less. That is very much not the case for an induction motor. That IE current that's flowing through our core is going to be somewhere between 30 and 50% of our input current, which means we no longer can just move that middle branch around at will because it's not so large that it looks like an open circuit compared to the other things, okay? So we're going to have to take that into account here in a moment, okay? So what we're going to wind up seeing, so one of the main differences between this model and the primary side of a transformer is the size of the parameters. And specifically, we're going to see that now XM is small. Before it was a very, very large magnetizing reactance. And we're going to see that X1 is large in comparison to what we saw in our previous examples dealing with transformers. So before we move along to the rotor side of the thing, are we okay with what all these different symbols mean and what they're contributing to and all that kind of good stuff? Give you guys a moment to catch up. All right. So now let's talk about the rotor side of things. And this is also on a per phase basis. And this is what we're going to treat our rotor like, even if it's a squirrel cage, because it's going to behave in the same way. Okay. So at a slip of S, the rotor is going to look like this. Okay. So here is our terminals of our rotor, essentially. And we are going to have a voltage here. This is going to be called SE2. We're going to have a reactance here, JSX2. And we're going to have a resistance here, R2. This is going to be our current, I2. So this is our secondary current, or essentially the current that's flowing through our rotor windings. And I want to make a note here that the rotor circuit operates at a frequency of F2 is equal to S times Fs. So I want to label what my things are really quickly. This one's a little bit easier, right? So R2 is the induced, the rotor resistance per phase, contributing to copper losses. X2 is the rotor leakage reactance. Per phase, obviously contributing to flux leakage. And then that voltage E2 is the induced voltage in the rotor at our frequency F2. So I'm going to have to transition to another page here, so I want to make sure you guys have a moment to catch up. Okay, so we can analyze this circuit and solve for our current I2. So literally, I have a voltage drop of SE2, and it is dropped across that reactance SX2 and that resistance R2, so this is literally just Ohm's law, I wind up getting a current of S times E2 divided by R2 plus JS X2. And this I2 is at our rotor frequency of F2, okay? So I want to quantify our copper losses real quick because we're going to see something that seems a little odd, okay? So P2, and I'm just putting CU here. This is my copper losses or my winding losses in my rotor. I'm considering asking you guys what you think it should be, but then I'm going to be disappointed. I'll do it anyway. So what do you guys think the copper losses are going to be? So let's start. So we have current and we have resistance. So how do I find power? Let's start there. We have current and we have resistance. I squared times R, right? Okay. So we're going to have the magnitude of I2 quantity squared times R2. And then we're going to multiply this guy by a factor of 3 because there are 3 phases. So that's where that factor of 3 is coming from. Now, this equation is a little bit misleading because it's not taking into account that slip is going to have an impact on our expression, okay? So what we can do is to account for slip, we can rewrite our current equation as follows. So we would have I2 is equal to E2 divided by R2 over S plus JX2, where this current for I2 is at our frequency of our stator windings. Okay. So this is the bridge essentially that we're going to use to go from our rotor circuit to our stator circuit, is just dividing through by S so that now everything is operating at the same frequency, because quite simply, we know up here, F2 is just F times Fs, our stator frequency. So if we divide everything by the slip, it looks like we're operating at our stator frequency. Okay. So at our stator frequency, then, we're going to have a slightly different equivalent circuit that we can use so that we can connect these guys together. Okay. So our new equivalent circuit, and I'm literally just dividing things through by S, what we're going to see is that we've got our terminals. So here's plus and minus. This is just our voltage E2. Here's our reactance JX2. And here is our resistance. And this is going to be R2 over S. And I'm going to put an arrow through this guy because effectively this is a variable resistance now. So the resistance of our rotor windings or our secondary windings are going to be dependent on the slip that we're operating at. So if our slip is very, very small, this resistance is going to look very, very large. And if our slip is effectively 100%, it's just going to look like the simple resistance itself. Okay. And this is our current I2, and this circuit is operating at frequency of Fs. Okay. So from here, our copper losses in our rotor windings are going to look like 3 times the magnitude of I2 squared times R2 over S, so that we see that our losses are indeed dependent on our slips. Okay. This power sorry, I made a mistake. There shouldn't have been a CU there. So this is not our copper losses specifically now. This is the total amount of power that has crossed the air gap. I apologize for that mistake. So this power represents the total power P mechanical plus PCU that crosses the air gap in the electromechanical energy conversion process. And we can play around with this guy. And so that's what the next little bit of math is going to be. And we can suss out from it some things. Okay. So rewriting, what we'll find is that our power delivered across the air gap and I'm now just going to start calling this the air gap power that I had drawn in the diagram. Okay. So the P2 that we just found is our air gap power. We know that this is 3 times the magnitude of our current squared times R2 over S. And I'm going to write this as 3 times the magnitude of I2 squared multiplied by a factor of R2 plus R2 over S times 1 minus S. So this seems like a weird thing that's going on here. What I'm attempting to do is to split these up into constituent parts. So just as a quick aside, you don't have to write this down. I'm just going to prove to you that this big ugly thing right here is literally just R2 over S, right? So we would have R2 plus R2 over S times 1 minus S is going to be equal to R2 plus R2 over S minus S times R2 over S. If I have this guy right here as S over S, then this guy right here cancels this guy right here, and I'm just left with the R2 over S that I started with. Okay, so just showing you how the math bears out. So now I'm going to split this guy up into those two constituent parts, so that we're going to have 3 times the magnitude of I2 squared times R2. And this was our copper losses that we calculated earlier. And so what's left, 3 times I2 squared times R2 over S times a factor of 1 minus S, has to be the mechanical power for our system. And from these relationships, we can see that our air gap power, PAG, is just 3 times the magnitude of I2 squared times R2 over S. And this is just our copper losses plus our mechanical power. Our copper losses can be written as 3 times the magnitude of I2 squared times RS. This is nothing more than S multiplied by our air gap power. So if we know our air gap power and we know our slip, we automatically know what losses we're seeing in our rotor windings. And then our mechanical power, three times the magnitude of I2 squared times RS over, excuse me, that S should have been an R2. My apologies. And this should also be an R2 times 1 minus S. This is just the same as 1 minus S multiplied by our air gap power. I'm going to put a box around these three because these are the main relationships that I want you to get out of these. And it's just simply, if we know the slip and we know any of those quantities, we should be able to figure out all of the other ones. All right, I'll pause for just a second and let you guys catch up, and then we're going to put these two models together. It's not going to get any better. All right. Oh, I thought I deleted this stuff. I guess I didn't. So let me get rid of this garbage from the previous example problem. Actually, that was only on one page. I'm just going to skip to page 5. That'll be easier. Okay, so our complete model. So this is a model with the entire circuit now operating at a frequency of F sub S. So everything is essentially working at stator frequencies. We're not concerned about our electrical frequency of our rotor anymore, okay? So our circuit model, myself a little more room there. It's going to be something like this. So here is the terminals that we apply our input power to. Working on the stator side of things, here is our stator resistance, our stator reactance. Here is our shunt components from our core resistance and our magnetizing reactance. I'm going to draw a dashed line through here. This dashed line literally represents our air gap, so that everything to the right of this dashed line is PAG. And now I'm putting my rotor bit on here. So we're going to have our rotor reactance, and we are going to have our rotor resistance, and I'm splitting these up into two different parts, and we'll talk about what that is in just a second. So I'm going to call this guy JX2 prime, where I'm using the prime designation because I'm referring that secondary reactance over to the primary side of our transformer model that we're using for our induction motor. So this would literally just be J times A2, or excuse me, A squared X2. Here we're going to have a resistance of R2 prime. And then this is the R2 prime over S times a factor of 1 minus S. So these are the two things that I expanded out so that we can see specifically a component attributed to core losses and then an opponent contributed to absorbed mechanical power. Okay. Where R2 prime over S is just A squared times R2 over S. And now we're going to identify our other signals. So we've got our current of I1 flowing like so. At this point, we're looking at the current that's flowing into our secondary. So this is going to be I2 prime since we're referring it to the primary side. This will be I2 over A. This voltage right here is still E1, but it is also A times E2. And I believe that is everything. So this is our complete model. So for what it's worth, we are going to treat our turns ratio for these guys essentially as if it were 1. We're not trying to step up and step down voltages and all of this kind of stuff. So we're just going to say, hey, turns ratio between the primary side and the secondary side is just 1. So that the A squareds and all of that kind of stuff literally do not matter. Okay, so we've got one more, I say little part here, but it is not remotely a little part. We have this model, and like our transformer equivalent circuit, we're going to try to do something to simplify this model, okay? Now, we can't simplify it as easily as we simplified our model with our transformer because we have that constraint to where our excitation current isn't just a small portion of our input current. So instead, what we're going to wind up having to do is use a Thevenin equivalent circuit. Okay. You guys talked about Thevenin equivalent circuits back in Ron's class, I hope. Feel like we talked about them a little bit at times in 280 and all that kind of stuff. Okay, well, too bad. Yeah. All right. So, yeah.
That alpha or mu under the I2 and I2 prime equation?
A for the turns ratio of the transformer, but that is just one. Yep. Okay, so Thevenin equivalent circuit. So the first thing that we're going to do is we are going to recognize that our magnetizing reactance is very small. We talked about that earlier when we were talking about the difference between our motor model for the stator and the transformer model that we dealt with when we were literally looking at transformers, right? So if XM is small in comparison to our core resistance, we can essentially just kind of not worry about it. So, or let me rephrase that in a different way. So we have an impedance. Let me scroll back down to our actual circuit here. Sorry. So we have this guy right here that is small, and this guy over here that is big, right? When we were dealing with transformer equivalent circuits, we saw that the resistance of our core was typically on the order of tens to hundreds of kiloohms, right? If JXM is a much smaller impedance, what happens when I have two impedances in parallel and one is much smaller than the other? Or what happens when I have two resistors in parallel and one is much smaller than the other? Let's start there. So if I have, let's say, a 5 ohm resistor in parallel with a 5 kilo ohm resistor, you guys have calculators in front of you. What do I get? Pretty close to the 5, exactly right. So when I have parallel resistances, it's always going to be smaller than the smallest resistance, but if there's a huge difference between them, it's going to be just under the smallest resistance, meaning that I'm just going to lump these core losses in with something else so that I don't have to add that to my circuit anymore, okay? So since RC is much, much larger than JXM, we can simplify our circuit by removing RC and lump the core losses in with the friction and windage losses and the stray losses. And we're going to call these rotational losses. So P rotational, or I'll probably abbreviate it as P ROT, is just going to be the sum of the friction and windage losses we've already talked about, the stray losses we've already talked about, and now our core losses as well. This lets us get rid of that RC. So now I'm going to redraw this equivalent circuit with what we have left. And this guy has a special name. It is not dumb, Zach. Friction and windage losses. So here's R1, JX1. Now our shunt branch is literally just, sorry, that should be a coil or an inductance. JXM. Here is JX2 prime. And for simplification's sake right now, I'm just going to call this R2 over S prime. This is our circuit. And once again, everything to the right of this dashed line, or this dashed line represents our air gap. This is what's known as the Steinmetz. And this is the IEEE recommended equivalent circuit. Okay. So I haven't done a whole lot of research on this guy Steinmetz, but you might remember his name from the lecture video I had you guys watch when I was sick, because he was the guy that also came up with the equations for the core losses and all of that kind of good stuff as well. So it's out of his research that we get this simplified model. Okay. Now, we are going to simplify this further by applying Thevenin's theorem to this to make it a little bit easier to manage. Okay. So what we're going to do is we are going to find the Thevenin equivalent circuit for everything over here to the left of the air gap. And then we are just going to replace everything to the left of the air gap with this equivalent circuit. So, as a refresher, in order to find our Thevenin equivalent circuit, the first thing that we're going to need to do is find our Thevenin equivalent voltage, VTH. So the circuit that we are interested in is this guy right here. So we have some voltage V1. Here is our resistance R1. Here is our reactance JX1. Here is our reactance JXM. Here are the open circuited terminals that we're finding the Thevenin voltage with respect to. So this is our VTH. Okay. So we can find this voltage VTH just by doing voltage division, because all I have is a bunch of impedances connected in series. So voltage division makes this a very, very easy process. So we would have our Thevenin equivalent voltage, VThev. Actually, I just called it V. Let me call it VThev up here as well, just so that I'm consistent. My apologies. Is simply going to be V1 multiplied by JXM, that's the element I'm finding the voltage drop over R1 plus J times X1 plus XM added together. And from this guy, we could say that the magnitude of my Thevenin voltage is just going to be the magnitude of my input voltage V1 multiplied by XM over the square root of R1 squared plus X1 plus XM quantity squared. Now, since R1 squared is usually much smaller than X1 plus XM quantity squared, we can actually simplify this a little bit further. And we would find that our magnitude of our Thevenin voltage will be approximately equal to the magnitude of our input voltage V1 multiplied by XM over X1 plus XM. Okay. I'm going to put a note here so that when you guys do your homeworks and things like that, I'm just going to say specifically this approximation is valid only when R1 squared is much less than X1 plus XM squared. So you know whether or not to use it. For what it's worth, I pretty much never use it because I do all of my crap on a computer. So it won't wind up introducing a huge amount of error by using it, but I just want you to know that when you're doing your homeworks, if my answer and your answer are very close but are slightly different, I'd be willing to bet it's because I didn't use the approximation. I don't have any beef with you guys using the approximation, I want to be clear, but because I do all of the work on a computer, I don't approximate shit. Okay. So I'm going to annoy you guys yet again and ask you a question. So how would we go about finding the Thevenin impedance here? Anybody remember the process for finding the Thevenin impedance? So Thevenin voltage was finding the voltage drop across the open circuit terminals with a live network, where I'm saying that we are exciting our circuit with some voltage V1, okay? To find the Thevenin impedance, we need to look into those open circuited terminals at a dead network, meaning that we're going to replace that voltage V1 with a short circuit. So I'm not going to bother drawing that out because I have a pretty, or at least I hope, we can look at this thing and see what it would be if V1 were a short circuit. So Nick, you nodded your head in agreement. So what do we see?
R1, JX1 are in series and it's parallel to JX.
Exactly right. That is all it is. So our Thevenin equivalent impedance is just going to be this branch in parallel with this branch when we short these guys out.
Oh,
Yeah. So we have to turn off the source voltage and we're looking into those terminals on the right, Baylor. So Z Thevenin is just doing parallel impedance combination here. This is just JXM times R1 plus JX1. And now I'm going to add those guys together, and that's just going to look like R1 plus JX1 plus XM, like so. And then we're going to simplify this a little bit as well. So this is the thing that I would usually use, and now we're going to talk about, again, assumptions that we could make to make the math a little faster, but lose a little bit of accuracy. Okay. So since R1 squared is much less than X1 plus XM squared for most cases, and X1 is much less than XM, our Thevenin equivalent impedance can be approximated as R1 multiplied by XM over X1 plus XM plus JX1, where this guy right here is our Thevenin resistance, and this guy right here is J times our Thevenin reactance. And again, only valid for the assumptions defined above. So putting these things together, the Thevenin equivalent circuit model is simply, here's our Thevenin voltage. It's taking the place of our input voltage. Here's R Thev. Here's JX Thev. This dashed line represents our air gap. Once again, this is where we disconnected that network. Effectively, our stator network found the Thevenin equivalent. And now we have our rotor equivalent circuit referred to our primary side. So JX2 prime in series with R2 over S prime. So this is our new equivalent circuit. It is literally just 4 elements connected in series. So much less gross than what we were actually using for our transformers. I just want to indicate here that this is our current I2 prime. And so what I want us to do now is figure out those power relationships and all of that kind of stuff using this equivalent circuit model. Okay. So using Ohm's law, we could say that I2 prime is just our Thevenin voltage over R Thev plus R2 prime over S. Sorry, that S looks particularly shitty. Plus J X Thev plus X2 prime. And then our magnitude of our current I2 prime is just the magnitude of our Thevenin voltage over the square root of those terms squared. So that's going to be R Thev plus R2 prime over S quantity squared plus X Thev plus X2 prime quantity squared. And from this, our air gap power, using our equation from before, 3 times the magnitude of I2 prime squared times R2 prime over S becomes 3 times the magnitude of our Thevenin voltage, quantity squared, times R2 prime over S, divided by R Thev plus R2 prime over S plus X Thev plus X2 prime. This guy is squared. So I squared it, right? So I have this I2 guy, or the magnitude of I2. When I'm calculating my power, I square it, and so that's going to get rid of that square root sign. I know you guys have put up with a lot of math from me today. Actually, it's not even a lot of math, it's a lot of equations stuff. I'm trying to decide whether I want to finish 20 minutes early today, and then wind up giving you a couple of equations at the beginning of class next time, or if I want to just finish up the equations and then all we do on our next class is see how we apply this stuff with example problems. So do you guys have a preference? Leave. Is that your preference? Okay.
Either way.
It's gonna suck either way.
Yeah, same.
Okay.
All
All right, it'll suck later on Tuesday then. All right, we're done for today.
It's like I had to stop writing, can you answer sheet 4?
Yep, I was writing for 90 minutes straight, so yes.
About one of the claims we made.
So we said since RC was vastly greater than JXM, we simplified and cut out RC, right? Where I'm confused is then we made similar statements say, oh, put too far. Basically, we made similar statements saying that if R1 squared was significantly less than X1 plus XM squared, we got rid of.
So we're not getting rid of it in our model, we're getting rid of it in our math to make the way that we calculate Z7 a little bit easier.
Right.
So essentially, if we looked at, so let's look at some things here really quickly, just from an example problem.
Because I'm just interested in how it flipped.
So XM for a motor is going to be several ohms, but it's not going to be hundreds or thousands or even, like earlier, I think we were dealing with, tens of kilo ohms or right?
Yeah.
So this is literally 1,000 times smaller than it. So that's why this guy throws the RC effectively away.
Okay.
But if we look at the value of the resistance for our primary windings, that was usually on the order of less than an ohm. So even though this is way smaller, it's still much bigger than that guy.
Oh, okay. Okay. So it follows sort of a path
Yeah.
down towards the smaller factor.
Yeah.
Okay. Got it. That makes more sense.
Yep.
Thank you.
You too.